All right, let's get started. Welcome to the session on Demystifying Invoke Dynamic. My name is Venkat Subramaniam. We're going to talk about this particular feature in Java 7 and how it took shape in Java 8. But before I get started, a word of caution. And if you have ambitions of using something you learned in this session on Monday, you're not going to be able to do that. This session is absolutely useless. So if you want to go attend another session where you will learn something that you can actually use, feel free to leave. I won't be offended at all. But if you're one of those people who are kind of curious to say, I really want to know what's under the hood, I'm kind of curious, I want to learn about all these stuff that I don't need to use, then you're in the right place. So you've been warned. We're going to talk about a feature that is at the bytecode level. It's a very fascinating feature to learn about. And it is a feature that helps us to answer a few questions along the way when we have the questions like, oh, I wonder what the performance would be. So let's talk about this a little bit. The invoke, best time to ask a question or make a comment is when you have it. So please don't wait till the end. Anytime is a great time. Draw my attention, say something so I know you're talking, so I can listen to you and respond back. So invoke, if you look at the bytecode, at the JVM bytecode, there are about 200 different instructions in the bytecode. Out of those, there are only 4 that really matters when it comes to making method calls. And the 4 really are going to be invoke static, which is used to call static methods, invoke virtual, which is to call virtual methods, invoke special, which is to call really private methods and constructors, and then you have invoke interface to make a call through interfaces. But I'm going to start with a little quiz for you. So I'm going to go ahead and say public void, let's say foo, and foo is, as you can see, a method which is going to simply, I'm going to just print out foo called. So we have this method called foo, and I'm going to call this method. So I'm going to say new sample, create an object of this class sample, and say sample.foo, and call this instance method, as you can see. Extremely simple example. So in this example, as we can see, we invoke the foo method. It said foo call. Life seems to be good. Let's get down to where real fun is. I'm going to go to the bytecode level. So in the directory here, you can see that the sample class is sitting nicely and happily. So I'm going to say Java P -C option. I already have set up -C as a alias for Java P, so I'm not using it. But anytime you use Java P, I'm using Java P -C here. And then I'm going to go to the location where the sample class is, and I'm going to take a look at this for a second. And if you notice right here, we are calling the method foo, and this should be of no surprise to us at all. You can see invoke virtual nicely, happily sitting here. It's calling invoke virtual. Why? Because foo is a virtual method. No problem, right? Excellent. Let's get back a little bit to here. And I'm going to mark this method as final. And we all know what a final method is. A final method is a method we cannot override. So here's my quiz for you. I'm going to go back and look at the bytecode right now to call this final method. And what do you think is going to be the call this time? Invoke special, because it's not virtual method, right? So invoke special seems to be a logical option among these, because invoke interface doesn't make any sense. We're not going through an interface. Invoke static doesn't make any sense because we're not calling a static method. Invoke virtual doesn't make any sense because we're not calling a virtual method. So let's get back to the code, and I want to make sure we really are using this implementation. So I've got to put 2 exclamations. Let's run the code one more time to make sure the code is compiled. Yes, it is. Let's get back here and invoke Java P one more time and take a look at the code. And the bytecode tells us that right now we are calling what? Invoke virtual. I felt like I was cheated the first time I ran into it. Do you feel that way too? You want your money back, isn't it? It's like, wait, why is it invoke virtual? After all, it's not a virtual method. Well, enters the problem. There are 2 compilers in Java. One is Java C, The compiler we use to compile the bytecode, the source code into bytecode, and the second compiler is the JIT compiler, the just-in-time compiler that takes the bytecode and creates the native code as we run the application. Well, it turns out there are a couple of interesting things that are happening here. The first thing is that when you call a virtual method, so like I had the foo earlier as a virtual function, or virtual method. When you have it as a virtual method, the compiler creates an invoke virtual. The JIT compiler comes along, looks at invoke virtual, and it says, hang on a second, this is a virtual method, but let me look around. And it looks around and finds absolutely no class that implements this particular class, extends this particular class. There's no class right now that overrides this method. And the JIT compiler says, invoke virtual, throws it away, and inlines the call directly if possible, or directly makes a call to that function where it's appropriate. Maybe 10-15 minutes goes along, and then you load another class into the virtual machine while it's running. The second class you loaded extends the first class and overrides the method. As soon as the JIT compiler notices this class being loaded, it says, oops, that optimization I did so far is no longer valid, isn't it? Scratch that, and then it rewires the call so that the call can now dispatch between the two calls, and that's only when the call becomes really virtual. But here's the trick. The Java C compiler knows that this is happening. So the Java C compiler says, wait a minute, hey JIT compiler, even if I put invoke virtual, darn it, you throw it away, so why should I do any more hard work? So even when the method is not virtual, it simply fires off an invoke virtual. And the JIT compiler looks at it, throws it away, but in this case, guess what? There would never be a class that overrides that method. So the optimization the JIT compiler does first is golden. It's never going to change. So this is a big conspiracy, isn't it? These two work hand in hand to perform really good optimization. So now you know why it's invoke virtual and not anything else. Making sense? So that is purely driven by the optimization. So now that we saw that, we saw how just one example of the JIT optimization that can happen. Well, it turns out that there's a lot of different optimizations that happen, but fundamentally at the bytecode level, the JIT compiler is one of the most statically typed compilers. When we complain about Java being statically typed and how it is statically typed, we are totally missing the point. The real culprit is the JVM JIT compiler, and the JIT compiler is very statically typed. So it turns out what's really happening is, when you call a method which is a static method, the invoke static says, stop right there, what are you calling? Well, I'm calling this method. Let me check to see if that method exists on this class. All right, got clearance for that. And who are you, by the way, making this call? Oh, I'm this call. Let me check if it's public. Okay, you have permission to call it. Now, turn your pockets. Do you have the right parameters to pass to this object? All these checks happen, and only when all these checks pass, the call is actually let through and the binding really happens to the method. Likewise, when you call the method invoke virtual, it goes through very similar checks. For invoke special, more checks obviously. For invoke's interface, what does it do? It makes sure the reference you have on your hand is actually an instance of the interface that you're trying to call this method through, and performs that check as well. So in other words, all these checks happen very quickly, but it happens as a result that JIT compiler is one of the most statically typed compilers that is around. Well, that's worked really good. But unfortunately, though, over the past about, give or take 10, 11 years, there are been other languages sprouting on the JVM. And some of these languages clearly are considered to be dynamically typed languages. Well, what's different in a dynamically typed language? In a dynamically typed language, either you don't specify what the type is, like in Clojure and JRuby, for example, or you can optionally specify the type, but you don't have to, like in Groovy. But in any case, the dynamically typed languages not only have this feature, they have another interesting feature, and that is metaprogramming. And that means you can inject methods into classes at runtime at will. And this means you will be able to call methods that don't exist at code writing time, but these methods come to life before those methods actually get called. So there is a time gap between when the compilation happens and when you make the call. Let's take a look at an example real quick to see how this works. I'm going to go here to example here in, let's go to Groovy for a minute. And here in Groovy, I want to write a very simple method. Let's go ahead and call this method over here as a call shout method. And this takes a string as a parameter. And within this method, I'm going to say print line stir.shout. And of course, something may go wrong. I'm going to print the exception details over here. So I'm going to say, oops, can't do it, right? So I'm going to go ahead and call the method. So I'm going to define, let's go ahead and say greet equals hello. And I'm going to call shout and pass greet to it. So if I run this little code, notice it said, oops, can't do it. And of course, we know why, because we know that Groovy doesn't have, Java doesn't have, Java lang string doesn't have the shout method. So that definitely failed in front of us. But notice what I'm going to do now. The call shout method is exactly the same method. I'm not changing it. But this time I'm going to say greet.metaclass.shout equals, and I'm going to go ahead and put this shout method, right? So that's like what you would do if you strike your toe on the door or something, right? That's how you're going to shout, isn't it? So call shout, I'm going to pass greet this time, and notice what just happened. It did not say, oops, can't do it, but instead it shouted. So the point really is, we are able to call a method which doesn't exist that failed the first time, but we injected that method into this class, and then we make the same exact method call, and this time the call goes right through. So the question is, how in the world can something like this actually happen? What's really going on? Well, you know one thing for sure. If you send this to bytecode using one of those 4 things we talked about, invoke special, invoke virtual, invoke static, and invoke interface, what's going to happen? The bytecode compiler, the JIT compiler is going to look at this call and say, hang on right there, wait for me a second, goes to the string and says, string, do you have a shout method? And the string says, what? And it comes to you and says, pew, and kicks you out, right? So there is absolutely no way to get through. And what do? Well, Groovy is smart. And what does it do? It says, if I make those four calls to the JIT compiler, it will refuse it, but I'm going to do something extremely brilliant. What is that brilliant? I've learned these things. I've got 2 children, and one is a teenager, and the other is almost a teenager. And you go to them and you ask a question. One thing rule about teenagers, right? They never give you a straight answer, right? You go to them and ask a question, they go blah, 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 blah for several minutes. And you listen to them and say, okay, I don't know if you answered my question. And you repeat your question, what do? Blah, 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 blah. And then after a few minutes, you're like, oh, whatever, and you walk away. This is a good trick on the teenager's part to get through and do things you don't permit them to do, right? That's kind of what Groovy knows to do. So let's look at what Groovy actually does at this point. So I'm going to go back to the command prompt for a minute, and I'm going to go to where my Groovy code is sitting, and I'm going to say groovy c sample.groovy, and I compile this code right here in Groovy. So if you look at the class files, the class file is sitting there, java p sample.class. Let's take a look at the class file. Are you ready? Here is the class file, and I'm not even going to increase the font size. In fact, I'm going to decrease the font size so that you cannot read it. Now, notice the code we have in front of us. This is Groovy in regular mode. I've not turned on the static compilation, obviously, in this case. And what do you see here? A lot of bytecode. That's like the teenagers talking to me, right? And the JIT compiler looks at this and says, okay, go right through, right? So in other words, you don't call the method, you call a method which calls a method, which calls a method, which calls a method, and basically through other APIs, you cannot get through. So that kind of seems work really well, isn't it? Well, the point really is, there is a demand from dynamic type languages. One solution is to use reflective APIs. Well, okay, you could use reflection, but unfortunately, that's a poor use of a tool. And what is the problem with that? The problem with that is, if you have one of those 4 method calls, there's a healthy dose of optimization that the JIT compiler can do for you. Instead of those 4, one of those 4 lines, if for each one of them, if you give boatload of 300 lines of bytecode, There is not a whole lot of optimization the bytecode compiler can do at that point, and as a result, some of these dynamic type languages can endure relatively poor performance compared to Java. So what can we do about it? Well, there are a couple of different options. The folks working on the JVM in Oracle had two options to deal with. One option is an option they have done before. They could completely ignore these other languages and pretend there is none of these that exist. And that would have worked okay. But instead, they took what I would like to call as an act of kindness. And they said, poor brothers over there who are writing code in these dynamic type languages, what could we do for them, right? And I can't express this with any other words than it's a mere act of kindness. And they took pity in the rest of us and said, let's do something for these folks. And they were thinking about how could we improve performance. And they came up with a brilliant idea. This is for Java 7, and this is changing completely when we talk about Java 8, but let's stick with Java 7 for a minute. So what did they do? They decided to solve this problem. How did they solve the problem? They solved the problem using one technique that David West talked about. It is called the one more level of indirection. In our field, we can almost solve any problem by introducing just one more level of indirection. So rather than calling that method, call a method which will call another method. Hey, that seems like an interesting idea. How does that really work? Well, the first thing is now we can do method pointers. I want you to celebrate this news because with that, Java finally has reached the status of sea level, right? Because we can have pointers finally. Well, okay, we've had method pointers for a very long time in our programming languages. You can do that in Java now. And that is basically a dynamic dispatch through it. This comes from the Invoke package. So what does that provide us? It provides us method handle. Now, you may ask, what does really mean Invoke Dynamic? What does it really mean? I want to talk a little bit about Invoke Dynamic. The Invoke Dynamic really has two parts. The Invoke Dynamic, as you can see here, has two parts. One is the invoke part, and the other is the dynamic part. The invoke basically says, I am interested in calling that method. It says, all right, stay cool. You can bind to something here, but I'll be very dynamic at runtime. I will decide what to call based on the context. That's the dynamic part. So think of this as taking the concept of polymorphism to the next level, if you will. Now, what is really invoke? How does invoke dynamic really do this? Invoke dynamic, I can express the word invoke dynamic in just a few words in English. Invoke dynamic means look the other way, right? Meaning, don't bother about type checking and all these details right now. Just pretend that everything is okay, look the other way. Go through, right? So what does it give you? I mean, you all will agree with me 100%. It is much more fun to get errors at runtime than at compile time, right? Absolutely. So this gives you that. So it gives you that wonderful glory where you not only can suffer, but it can make everybody else suffer in your teams as well, right? So this gives you that ability to postpone things to runtime. Well, okay, I'm just trying to be funny here, but it's got, trust me, it really has some benefits. So it really gives you that benefit to postpone this to a little bit of time and gives you that ability for you to postpone to a later time. Now, this comes from what's called a method handle. So what does a method handle really do? Let's start with a few examples, play with it, and let's see where this takes us to. Let's say for a minute, I'm going to have an instance method. I'll call it as inst method. And I'm going to say pass a double value. We'll call it as value. And I'm going to simply display here inst method called, let's say method called. And I'm going to say plus value, right? So I'll display that. Likewise, I'm going to go ahead and implement one other method. And in this method, I'm going to return the value. Let's say double, and I'm going to return the value times 2 so we can actually see what it's doing in this particular case. In the case of this method, I'm going to call it a static method. And I will mark this, of course, as static. And I'll get rid of the final. We don't care about it. We talked about it. And this is going to be the static method I'm going to use over here for us to call. Excellent. So we got a static method, we got an instance method. It's time for us to play with these. I could have said instance method like this directly, right? And once I do that, I could also have said sample, call the method on the class, and I could have said static method and sent a 4 like this. So we could do something along these lines, and of course when we run this code, we can see that the methods are called. But what fun is it to call the methods directly when you can call it indirectly, right? So what I'm going to do here is I'm going to first of all say look up, and I'm going to ask it for the method handles. So I'm going to ask it for getting the method handles from this. So what am I going to ask for in this particular case? So method handles, and I'm going to create the method handles object. So I'm going to call it as handles. And I'm going to ask it to give me a reference to the object. So I need a backdoor to get to this particular method. Now we have used reflection in the past, absolutely. We have done reflection. And what do you do in the case of reflection? You go to a class and say, hey class, do you have this method with these parameters? And it gives you a method object. And then you can go to the method object and say invoke, and you can pass the object and the parameters, and you can have it invoked. So that is reflection. But that only works really well when you have the methods that you are really talking to. But what if you're really interested in binding to methods that don't even exist? For example, remember the Groovy side, we called a method that doesn't even exist called the shout, but that may exist during runtime, but not during code compilation time. So how do we deal with situations like those that we can handle pretty nicely? So what I'm going to do is, I'm going to go ahead and ask for the lookup object right here, and that gives me a lookup object, and I'm going to say lookup dot, and I want to find a static method at this point. So I'm going to say lookup static, find static. Where am I looking for? In the sample.class, of course. And I'm going to ask for what method? Well, I'm interested in the method named static method. And of course, we have one other feature in Java we got to be careful. Remember how we have method overloading available in Java. Well, how do we deal with method overloading? Let's think about this for a minute. How many parameters can a method have? 0 or more. But so a method could have 0 parameters, it could have 1, it could have 2, it could have 3, and so on. But there's one thing that's always true of a method. It always has a return type. So what we do here to specify is we start with the return type to begin with. So we say method types over here, and we start with void.class because the static method is returning a void, and it takes one parameter, which is double.class. So we tell him what he has to return. Now, obviously, very promptly, the Java compiler tells us we need to be concerned about exceptions. We will give it the treatment that good programmers always give, which is simply to pop it up on the other side. So now that we have pushed it across, what do we do next? Let's go ahead and call this method. So I'm going to say, oh, we got to save this handle. So let's go ahead and save this handle into a static method handle. How about that? So we got a handle on our hand. So we're going to now say static method handle dot invoke. And what do I want to send to this guy? Well, this guy takes a double value. So let's go ahead and say 2.2 over here and call that. Well, the compiler again reminds us there are exceptions we have to handle. Not a problem, we can take care of that. So that is taken care as well. So we called a static method. Let's see if that works to begin with. So I run this code, and you can see the method was called right there. However, in this particular case I called with the invoke, there is also a version called invoke exact. And the invoke exact says, you better give me exactly what I want, because I am not going to spend my time and effort doing typecasting for you. So if you send a 2 instead of 2.2 to invoke exact, you really made it very mad, and it calls you by names, as you can see here, right? So that is 2 different options, but it depends on how much optimization you want from it. Invoke exact says, I've done type checking before, send it right through, versus invoke, could you do a little bit favor for me? I need some more help with you. So on the other hand, I'm going to say lookup over here dot find virtual. And in this case, the class is still sample. The method is called invoke, what is it called? Instance method, that's what we called. And then the parameters the method is taking is method types dot method type. And what's the first parameter? Well, it's double dot class. Remember the return type, and the input is a double dot class also. So we pass those two. And let's save this away into instance method handle right now. But there is a bit of a difference in this case. Instance method handle dot invoke exact. But this requires an instance of sample to begin with and the value that you want to pass. So those two required because we haven't told him what the object is that he has to use to call this method. So those two information are needed for it to work properly. Let's go back and take a look at what I did here to mess this up. So in this, of course, this one should be exact. I forgot to change that back. So let's go back and try this one more time. Let's see what the error says in this particular case. So in this case, it called that method fine. Let's get back to the main method here. He's complaining about not being able to call the second method on line 26. It is complaining. So let's look at line 26. That's when I make the call. So instance method handle. So we got the handle from that object. And I'm going to go back here. Let's go ahead and try the easier version first. So I'm going to say, first of all, go ahead and invoke this method for me. And what are the things it needs? It wants an object and arguments over here. So we got to do one more thing. We want to call this method. There are a couple of different things we could do. We could use a bind argument to bind this particular object if you are interested in. But in this case, I'm going to say sample is the object, 2 is the method I want to call. If that doesn't work, I'll switch back to the bind method and show you how that works. Okay, so there you can see how that worked. Alternately, what you could do is you could also say invoke handle dot bind to, and you can specify the sample right here. Then you don't have to give the sample now because the method handle you get from bind to has been bound to the instance method on that instance, so you no longer have to bind it again. And obviously you will store it into a variable and then reuse it after that. So that gives you an example of how you can go around and call it. Now, one question people often ask me at this time is, wait a minute, how is this different from reflection? Well, in reflection, of course, we normally ask for methods that do exist. In this particular example, those two methods do exist, so you could say that you could have used reflection for it. But like I mentioned, if you really want to bind this to arbitrary methods that don't exist, or this could be bound to something that's absolutely created on the fly while the program is running. I'm going to show you an example of that later. Reflection is not very convenient. You can think of method handles as reflection plus plus, or what reflection should have been really. And if reflection were to be done again entirely, it maybe will look like this. In fact, to understand how this is going to look like, let's look at one really interesting way to go back and forth between these two. So what I could do is I could do a lookup on this. So we have, well, actually, let's do it a little differently. We could go use reflection. So we could say, for example, sample dot class dot, let's say dot get method, and the method I'm interested in, let's say, is going to be the instance method as an example. Well, once you get the instance method, it tells you the double class is what we want. We could store that as inst method. Now this is a reflection API, as you know, but you can say lookup dot, and this is one of the most funny methods I've seen actually in this API. It is actually called unreflect. What a cool name, right? And so you're going to say instance method, and now you can get the method handle back on it. And then once you're unreflected, well, that sounds so weird. You can actually then go back and call the methods using this API as well. So we talked about how we can call these methods. Well, I promised you earlier that there will be absolutely nothing useful in this presentation, and I invite you to leave the room. And I don't think I saw anybody. In fact, there's one dude walking in right as I say it, right? So should we tell them or not? Just keep it quiet? Okay, cool. All right. So, and usually when I say that, about 10% of the room evacuates. That usually happens. So I'm a little surprised but thankful that you didn't leave. So I feel kind of tempted that I should give you something, maybe a little bit something that you actually can possibly use. So let me give you a little bit of what you could actually use. Now, there is a beautiful feature in languages like Groovy that I really wonder why Java doesn't have. Well, but we can actually implement it now. Let's see how. What is this feature I'm going to talk about? Well, this feature is called multi-methods, one of my most favorable features. What is a multi-method? Let's start with polymorphism for a minute. So what is polymorphism after all? Well, polymorphism says, go ahead and make a call on an object. So we got a target.foo with some parameters P1 and P2. Polymorphism says, go ahead and make this call, and at runtime, the method to call will be decided based on the runtime type of the target and not the compile time reference type of the target. That's how polymorphism works in almost every language, including Java. But multi-methods are polymorphism on steroids. This essentially says, go ahead and call the method at runtime, but the method I'm going to call is based on the runtime type of the target plus the runtime type of the parameters as well. So in other words, it can call the method not just based on the type of the target at runtime, but it examines the parameters and say, hey, your type is different. I'm going to call a different method for you at runtime. Let's think about what benefit this can give to us. I'll give you an example of the benefit, and then I'll go show you how we could actually do this in Java. So I was actually working on an application where we had to parse through a hierarchical structure. So we have, say we have nodes, and each node in a graph is just a node. We have then a class called node type 1, which extends over here from node itself. And then we also have similarly other types of node, right? So node type 2 and node type 3 and so on, right? So we got all these types of nodes available to us that we could actually use. Now the problem is this: when we have these different types of nodes available to us, we had to write code where we had to process different types of nodes. So we have a class called processor, and the processor had a method called handle. And the handle method, pardon me, this is an interface, and the interface processor had a method called handle, and guess what it took? It took a node as a parameter. Stay with this for a second. Now I have a class called processor, let's say processor 1, which is for node processor, let's say node processor 1. And what does processor 1 do? Well, it implements, obviously, the processor interface, and now I'm going to say void handle, and I'm going to say node type 1, because all I care about in the processor 1 is to handle only node type 1. Will this code work in Java? No, you're going to get a compilation error. And what does the error say? You need to implement handle with the node on it. So what do you normally do? You say node, and within this particular code, and what do you want to do here? If node is an instance of node type 1, then you do your work. Otherwise else, sit back and cry, right? So you are crying. Why? Because this is like, it'll never happen. Why am I doing this? Now it becomes even more fun. Later on, you have a class called processor X, which implements the processor. And this is a cool class. It can handle 3 types of these. So what do? Public void handle node. Why are you doing that? Because that's how the compiler will be happy, right? And then if node is an instance of node type 1, and then you go ahead and do whatever code, call other methods, and then you say if node is an instance of node type 2, and then you do other stuff over here. And then of course you will have another piece of code that says if the node is of node type 3, go ahead and do the other work here. And does that sound familiar? Right? Now, what do you do in this case? What you're doing here is you are doing what the compiler tells you that. If somebody looks at this code and say, that is smelly, you say, not me, I'm just doing what the compiler told me to do. So it feels like you're working for the compiler rather than the compiler is working for you, right? So that kind of happens along the way. But if you look at the highlighted code, what is that code symptomatic of? What style of programming is that? Well, that's right. It's okay. Say it loud. Procedural, right? I hear this word with defiance, right? It's like, I don't want to say it. I don't want to admit it here in public, but it's procedural code. Well, how did we suddenly end with procedural code in an object-oriented language? Supposed to give us polymorphism. Let's try this one more time. Well, when I do this in Groovy, I don't have to do all of this. I simply write one method called node type 1, and the compiler says, sit back, relax. I can call the method for you if the object is a node type 1 automatically. Similarly, in processor X, I would say node type 1. I will overload these methods with 2 and 3 types, and the compiler is smart enough to call the method automatically because polymorphism only looks at the target type. Multi-methods look at the target type and the type of the parameters as well. Let's see if we can do something like that here in Java. So I'm going to go back to Java here for a second. Let's entertain this thought for a minute in this example. So I'm going to go back to this code and say class, let's call this one as class base, and the base has a public void, let's say foo. And this is going to take a double value as a parameter, right? So I got a double value as a parameter, and I'm going to output right here simply base : foo. Now I'm going to go ahead and implement yet another class now. This class is going to be called as derived, and the derived class is extending from the base class. Now let's leave it at this for a second. I'm going to say this is going to be derived so we can actually look at it. So let's try this out. So I'm going to call this method public static void use takes a base object reference and base.foo and sends a 5 to it. So now I'm going to come back over here and I'm going to call this with 2 different parameters. So I'm going to say use new base and I'm going to say use new derived. So I'm going to call these 2 methods with these 2 objects. Well, actually it's complaining that I can't call this from a static scope. Not a problem. We'll fix that in a second. So let's get rid of that and let's simply say over here, we're going to say, yeah, why don't we do this? Void run, and within the run method, I call new base, and then I'm going to call use new derived, right? So I'm going to call this method with these 2 objects on my hand. So now that I called with derived over here, let's fix the spell here, derived. So we have, actually, which is the right spelling? Okay, so derived, okay, all right. You can kind of figure out English is not my language. All right, so there's derived right in both places. So right there is derived that we have written in both cases, and I want to call that method. So let's go ahead and say new sample, and we will simply call this method dot run, and let's go ahead and just fire this up, make sure everything is working as we expect. Yay, look at that. So we called the method first with a base object, the second time with a derived object. So as you would expect, this code is polymorphic. We're using a base object reference. So the first time when we sent a base object, it went to this method. The second time when we sent the derived object, thanks to polymorphism, it went to the derived foo method, as you can see here. So when we go ahead and run this, you can see it says base foo and derived foo as appropriate. Let's do one more thing. I'm going to change this to int value right here. So that's the only change I just made. So what did I do? The base is taking a foo with a double. The derived is taking a foo with an int. That's the only change I made. But this part is still the same. It's calling base.foo. I'm calling base derived, new derived, with sending it to use. What do you think is going to be the output on this call? Well, I'll answer that for you. It's going to be base derived. Yay. What do you think is going to be here? Base derived also. So when you run this again, notice the shock here, right? They both ended up with the base derived. What happened to the function in the derived object? It never went to it. You may wonder, aha, I know the answer. It's no longer invoke virtual. Well, we addressed that question in the beginning of the session already, right? So if you dig into the bytecode and look at it, it is going to be invoke virtual, so that's not the reason. The reason for that is, again at the bytecode level, it may be interesting to look at it one more time. So let's go back and look at the bytecode one more time. And if you look at the bytecode this time, you would notice something weird going on here. Well, notice that in the use method, there is the invoke virtual as I promised. However, notice this D over here. So what's really happening? What's really happening here is the compiler says, aha, I'm going to call this method called foo. It is virtual. However, hang on a second. Hey, base, do you have a foo method? Says, oh, I do. Bring it on. And what does the foo method want? and it says, well, I want a double. And the compiler says, no worries, I will convert the int to a double right now at compilation time. And notice right there is a conversion of int double. The conversion is over. Remember what Frederick Brooks said, premature optimization is the root of all evil. And it said, I'm done, right? So at runtime, you walked up with an int, and the compiler says, I don't care, convert it to double, and then says, do you have a method called double, right? Foo which takes double. And sure, there is a method called foo which takes a double, and where is it? In the base class, not in the derived. That is why it polymorphically calls that. Let's say how we can change this with what we have learned in this session so far. So I'm going to show you how we could use this to do method handles. So I'm going to get back to this code over here, and this time I'm going to say call the method, and call the method is going to take, first of all, I'm going to call the foo method. I'm going to send a 5, but I'm going to say double.class. That's all I'm going to send to the call the method. Well, I would need an object also, so let's go ahead and say sample, or this is the object that I want to call this on, right? So let's get rid of these guys. We know that it was calling the same method. We'll discard that. So what I'm going to do is call the method. I send the object. I send the value. I send the double. Let's go ahead and write this method called the call the method. Well, what am I going to do in the call the method? I want to take the instance I want to work with. So I'm going to say object instance. And in this case, I want to take the data. I'll say object data. I don't care about what the type of the data is. And class is going to be data type here. So once again, I'm going to change it to, in this particular case, I'm going to say that this is going to be just a question to say that I don't know what the type is right now. So what am I going to do? I got the sample object. So I'll say method handles dot lookup, and I'm going to do this twice in the call. I'm not talking about efficiency. I'm just focused on behavior at this point. So I'm going to go ahead and implement the lookup, and I'm going to say lookup. What am I looking for? Find a virtual method. Where am I looking for? In the data type class, right? Okay, what's the name of the method? Well, that's called foo, we know. What's the method types over here? Well, we know the method type information also. The method is returning. I don't remember what it's returning now. So let's go back and find out. Oh, those methods are returning a void. So we can simply say void dot class. And the type that it's going to take is the input type, right? Data type. That is what I'm going to send over here. So I've made a mistake. I'll come back and fix it. So this is the data type I want to pass to this method. So in this case, what I meant was I wanted to say it is going to be this dot get class, right? The method is on the object given to us. The foo method and the return type, the parameter type is the data type. Well, that's great. Now what do I want to do? Now that I have this lookup on my hand, I'm going to store the handle, and I'm going to say foo dot invoke. And where am I going to invoke it on? I'm going to invoke it on the current object, this, and the parameter is the data that I have to pass to it. So let's propagate the exception along to report it up there, and that's what we are just doing right now. Let's try this little example before we go any further. So I'm running this code, and I've got an exception to deal with. Line number 28, it's not happy. Let's go fix this. So find virtual, and I'm asking you to find the virtual method on the lookup. And the object is this dot get class, which is going to be the sample class. The method name is foo, and the method type is going to be a void method, and the parameter is going to be the data type we received, which is going to be the double dot class. Let's see what the error tells us now. No such method exception, no such method foo on the object, in this case invoke virtual, is reporting for us on this particular method object. Let's make sure that I send the right things. So we have the base object, so that is going to be, so sorry, I understand what I did wrong. So let's get back to this code right here, and what I meant was this should actually go into the use method, or we could do it on the sample. Let's do it on the sample. There we go. So this should be new sample after all, right? So let's say sample. Yeah, because this was the other object at this time, so this should be the current object, which is the derived object. So there we go. So instance. Yeah, my mind needs to rewire what I'm doing. Okay, so here is the instance I'm interested in. So new derived, and I'm going to say this is going to be the instance I'm interested in. So we'll call it instance. There we go. So now we can run this code, and we can see that that particular method, well, let's see what this error says. It is persistent with me, isn't it? Correct. So, well, actually, it should be instance. So, which is this guy. Yeah, thank you for waking me up there. Go ahead with your question. What was that? What line number? One line up. All right. That should be a instance as well. Yeah. So don't let me talk and sleep. Okay. Excellent. Thanks. So that is the instance we are dealing with. Yeah. Let's see how it works. Okay. Well, what am I doing here? In this case, I want to change this to, remember on the derived object, it ended up calling the base.foo all the time. I'm going to pass an int to class right now. And let's see in this case what it does. Yay, finally, right? So it's the same instance, but we are able to get two different calls on it. And we are still sending 5 to both, as you can see, but we are able to send the type in here. So I just emulated multi-methods here in Java using this example. Well, think of the benefit that this gives you. This gives you the ability to really dynamically implement only overloading and dispatch method calls. And so as a result, you don't have to go through that kind of interfaces. Life can become easy. You could also use reflection to do this as well, but this kind of gives you a bit of a benefit that you're letting the JIT compiler deal with it more efficiently. All right, so let's talk about call sites. We were talking about the invoke part so far. We haven't talked about the dynamic part yet. So we know how to invoke the method, but where does the dynamic come from? Well, the dynamic comes from what is called a call site. So what is a call site? Well, it's like what you do. You say, I don't want to call this method. I'll call this method, which will in turn call this method. So this is what a call site does. And in order to understand call site, I want to use an example that we can relate to really well. Well, take the wonderful railway system here in Europe. I love traveling in trains when I'm in Europe. And when you look at trains, there is something that trains do very nicely. They got network of tracks that they have laid out. And trains travel at a very high speed on this network of tracks, and most of the time they stay on the tracks. Now, when they do, when the train is going fast, the driver very rarely has to care about what track they have to travel on. They have to only travel on one track, right? And the track that they are on right now. But before the train gets to a certain point, there is an engineer out there. What does this engineer do? Presses a few buttons or moves a lever and converts this track to go, let's say, to the right. And the fast approaching train, what does it do? It zips through the track and goes to the right. And a few minutes later, the signal turns, the engineer comes over and looks at the schedule, and it says, well, the next train is going to go, west or to the left, and the engineer presses the right button, and the track rewires, right? So that track is still there, but the track configuration rewires, and now the train approaching very fast will go to the left rather than going to the right. But the driver didn't care about it, right? Well, the engineer had to rewire it. If you understand how that is kind of analogical to what we're going to see, you know what call site is all about. So when your program is running, you let the call site bind to implementation 1 of a method. You keep calling the method non-stop, and you keep firing at it, and guess where it goes? Method number 1. And along the way you say, hey, I'm using metaprogramming, I'm going to rewire this method. I don't want method 1 anymore, I want method 2 from now on. Guess what's going to happen? The call doesn't change a bit, but the JIT compiler walks over and flips a switch, and it's going to go to method 2. The next time you call the method will end up in method 2 rather than method 1, just like how a train will take a different track because rewired the switch. Does that make sense? So let's look at an example of how that's going to work here with a call site. Well, there are 3 types of call sites. The first call site is called a constant call site. As the name indicates, a constant call site is going to be bind once. So at the beginning, it's not bounded. At runtime, you say, you remember this call site you have? Well, no call has been made yet. We're about to make a call, bind. And once you bind it, it's a constant binding. It's not going to change anymore. It's attached to it. Now, what is the benefit of constant call site? Very good performance for things that are not going to change. Once you're going to decide at runtime and bind to it, you're never going to change it. So this is very efficient. No need for concurrency checks on it, because once it's bound forever. You don't have to worry about multi-threading. The second solution this offers here is called a mutable call site. A mutable call site, as the name indicates, is what you can bind and you can change, and you can bind and you can change. Now, obviously, the good news here is it can change, and so you can bind and rebind it. Well, how do they solve a concurrency issue? They solve concurrency issue in one of the best ways you can imagine. They said it's your problem, right? So you have to deal with this if you want to take care of this. So if you're in a single-threaded application, no problem. If you're a multi-threaded application, find another job, right? So that becomes a real issue to deal with. Volatile call site, on the other hand, says, I'm going to mark this as volatile, so every single action will go to the main memory to get this, so concurrency issue is solved at the expense of going to the main memory like a volatile variable normally is. So those are the three solutions. So what I'm going to do is I'm going to quickly show you an example of how this is going to be with one very simple example here, just to understand a little binding. Let's look at a couple of different examples, right? You would not write code like this in Java typically because this is all done at the compiler level, but it's kind of interesting to get a feel for how this would look like. So I'm going to write a static method here called a tick, and the tick method, as you would imagine, simply says tick. I'm also going to write a method over here called the talk, and as you would imagine, the talk method simply says talk. So I got two methods on my hand, or both of them are static methods. So now I'm going to say create handle, and the create handle method is going to return a handle for me. So I'm going to go ahead and call the create handle method. Well, the create handle method is going to do a couple of different things. It first says method handles, and I'm going to say lookup and get the lookup object, and then I'm going to say lookup dot find static on what? A sample class, and I'm going to say the method I'm interested in is called the tick method. And what does it take as a parameter? Well, method types over here in this case doesn't take anything, so void.class is all I'm going to send to it, and I'm going to store this away into a tick handle. So let's call it as a tick handle, and this tick handle is going to be a field in the class. So I'm going to go ahead and create a field in the class called a tick handle. Similarly, I'm going to create a talk handle, which we're going to use in just a second. So let's get back to the code right now. And in this case, we created a handle. The next step is, of course, to say lookup.find static again. This is going to be sample.class, and the method is talk at this point. And method types over here, again, is a void.class. And I'm going to store it away, as you would expect, into a talk handle, right? So great. So we saved it into those two variables right now. The last thing I want to do is return a new call site, and the call site I'm going to return is going to have a method handle. So I'm going to say a tick handle as the handle I'm going to return with it. So now that we have all these things available for us, it is time for us to go ahead and implement this particular method for ourselves. So let's do that. Let me take care of that for a second. It's complaining about using the wrong stuff. So we'll say new mutable call site, of course. And then I'm going to say this is going to be the tick handle, right? Yeah, there we go. So we created the handle. We're returning stuff. Let's make the compiler happy real quick, and then we'll move on. So we created a handle, and we are passing it around. Let's take care of the exception at this point. Let's see what this error says. So it says cannot return a value of this, of course, because there should be a call site that I want to return. Awesome. So now that we have this, let's save this here real quick and make one call. So I'm going to say handle dot, and I'm going to ask it to invoke the method. So invoke, what do I want to invoke at this point? Well, this is the call site, get target dot invoke. And in fact, let's go ahead and save this away before we go any further. So we will call this as the handle itself. So this is the call site, and I'm going to save this away here. So call site, and I'll save this as a handle here for us. So handle, there we go. And handle dot invoke, and what am I interested in invoking? Just the method on what? I will call it as on an instance. So we'll get to the instance in just a second. So the instance is going to be just a local variable on sample that I want to create, and we will say it's equal to new sample. There we go, right? So let's just try that one little example for a minute. So you can see in this particular case, we called the handle and obtained the handle on this. It says wrong type, method type exception. Let's see what the error is. Did I say static? Yeah, I did get static methods on the tick and the talk. Does anybody see the error I made? That is correct. So that is the, we don't need the instance because we already called the object. That is correct. Thank you for helping me with that. So that's the handle, and it's a static method, of course, right? So let's go back and run this, and what does it do? Hey, it said tick. Let's do one more thing. Let's go ahead and say in here, we'll just iterate for, how many times? Let's say 10 times. So for 10 times, I'm going to call this method handle. So notice this code is not going to change. We could put this in another method if I wanted to, right? And then we'll say thread.sleep, and let's say 1,000, and we will just call that. So you can see that in this case, it's going to call tick about every second. But while this is doing this, let's go ahead and change this method just a little bit. Let's go back to this code. Right after this, we will say change handle, and in this case, I'm going to send the call site over to it. Notice I'm not messing with this handle. I'm not changing that handle at all. In fact, I'm just passing the call site. So in the change handle method, what I'm going to do is simply say, something along these lines. How about passing the index as well? So let's say comma index. So in here, I'm going to receive the index. So we'll say comma int index, and we'll simply say if the index is mod 2 is equal to, actually we'll do better than that. We'll say call site dot get target is equal to a tick handle. So if it is a tick handle, what do I want to do? I'm going to say call site dot, and I'm going to get over here for a second before I forget. I'll say get over in the call site. We'll say, actually that's still fine. We'll come back to that if needed. So call site, and I'm going to say dot and set target to a talk handle. Otherwise, else, we will set it to, let's call it as set target to a tick handle. So let's go ahead and try that now. We didn't change the handle itself. Instead, we changed the call site, right? That's what we changed. So right here, obviously, that didn't quite take effect. That's what I wanted to look up here. So we go back to the call site and say dot, and we will call this as dynamic invoker. So this gives us an ability to really say, don't bind to the handle ahead of time. Now, look at this in this case. It goes tick and talk back and forth, but I'm going to do one more thing just to show you how really dynamic we can get to. The last step I want to show you here is if the index is equal to 8, let's say. What do I want to do at this point? Well, now that I'm in the last call, I'm going to say call site.setTarget. We'll call it as local handle. Now, what in the world is this local handle? So I'm going to say runnable. We'll call it runnable equals. And I'm going to say just an output. Output will say tada, right? So that's our lambda that we just created. And of course, I know a few things now. Look, we'll go to method handles and go to lookup. And we will tell the lookup now. We'll say lookup dot, and I want a virtual on what? Runnable dot get class. What's the method you want to run? What is its method types? Well, method type is void dot class. So that's the method handle I want. So we'll save that into a method handle. We'll call it handle. And now what do I want to do? I want to say handle dot bind to the runnable, and I'm going to get the local handle that I'm interested in, right? So we got a local handle on this guy. Well, exceptions, of course. Let's go ahead and just send it up. And in this case, we got the last call where we are toggling this. So let's come back to the code one more time. So here's the code where we're using the handle repeatedly. So if we run this code, you can see you got a tick and a talk, but hopefully if I didn't mess up writing this code, the very last call should be to the local handle we created. And as a result, it switches over to the last object. So you can get to a fairly good dynamic behavior with this. Like I promised, you would never do anything like this in Java. And if you're at work and you see a colleague do it, stop the colleague from doing it, right? So this is really for lower level things. But I want to wrap this up, if you will allow me about 2 to 3 more minutes. I want to wrap this up with one final detail. Well, if we leave the talk right now, we would leave the room with one impression. Okay, they got together, they did an act of kindness and helped the brothers doing programming dynamic type languages. Well, this completely took a turn. when they started working on lambda expressions, they were in trouble because they were asking, how in the world are we going to implement lambda expressions? And as they were thinking through it, some really interesting thoughts that came to their mind. So this is after Java 7 and while they were working on Java 8, right? Again, this was done for dynamic type languages in the beginning, but that drastically changed as you're going to see in the discussion right now. So going back to this example here, let's go to one simple code. Remember what we could do in the days past. We could simply do something along these lines. If we had, for example, let's say a java.util.star and bring in all the collections. Let's say we have a list of integer and I have some things called numbers, let's say. And I say equal to arrays.asList, and let's just pick up these three numbers. Well, in the days past, we would use anonymous inner classes, right? Now, numbers.forEach, one of the beauties of this is you could say new consumer integer, for example, and then you could have written code like this. You would have said integer is that interface I'm interested in implementing, and here is the accept method, and then you could output right here the accept method. You could say value, where value is the value passed into you. So when you run this code, you can see that in this case it printed 1, 2, and 3. However, instead of sending an anonymous inner class, you could do the following. You could say numbers.forEach and simply send value, and then you can output just the value itself. So notice how sweet this code is in lambda expressions. So the fact that these two work may quickly help us, maybe lead us to think, oh, this is kind of cool. Anywhere you can use a single abstract method interface or an anonymous inner class for it, you can simply use a lambda expression. Cool, right? Now that is a very troublesome thought. And the reason it's a troublesome thought is, let's think about just an example. Let's assume for a minute, all they do is do a compiler syntax sugar where they take this code and simply spit this before they send it to the JIT compiler. What's going to happen if they do it? Well, let's compile this code for a second. Now, when we compile this code, let's go over here. We don't have to look too far. Let's just do a ls right here on this code right here. And notice what happened here on the sample. Notice how many samples are there. One sample and one sample, $1. You know where the $1 came from, right? It's kind of funny that inner classes really are not inner, right? Okay, but if all they did was the syntax sugar, what's going to happen? You come along and say, dude, this lambda expression is really cool. How concise it is. We can do that now. So you wrote that many. And what would the compiler do then? The compiler would simply say, no worries, and it would do that. And if it does that, what will happen? Well, your code will be concise to a human eye, but when you come down here, it'll be an explosion, right? And nobody in the right mind would go home happy with it because your jar files became just bigger, your loading time became bigger, you have introduced so many other problems to deal with. So they're sitting and scratching their head, what can we do about it? And somebody came up with an idea which only can be called as crazy. And they said, hey, what if we use invoke dynamic? And I was like, what? And suddenly they realized, cool, we could actually do that. And suddenly the feature that started as an act of kindness became the most important feature for Java 8. And if there's one thing I learned from this, it's called filling your karma bank. If you do the right things, it comes back to you, right? So that's a karma bank. So notice what they did. They went back to this and said, oh, let's do something a little different. Because this is so cool, we could actually do this so many times. So I'm going to uncomment this code, and I'm going to leave this code, the old code, away here, as you can see, right? So remove that. So now I go run the code, and notice what happened. It produced all that output, as we can see. But I go back to the disk, and guess what? Look at that silence. And there is some amount of peace in silence, isn't it? And if you open this and say java p minus c and output sample.class and take a look at it, notice the beauty of this. They all simply quietly turned into an invoke dynamic, as you can see right here. So each of the methods became invoke dynamic. So what started out as a feature to help dynamic type languages ended up being one of the features that Java 8 heavily relies upon. I really hope you find that absolutely useless. Thank you. Cheers.